Welcome to Spring LIB.
In this problem, we have a circular region of radius r equal to 3 centimeters in which electric flux is actually going on. So let us draw a circular region. This is a circular region. It has radius r. There is an electric field which is resulting in a net electric flux. So I'll write as phi E. In this case refers to, so this flux is due to the electric field. And as we said that this is actually varying. So the variation of electric flux to this is given 6 volt meter per second, 0.6 volt meter per second. And it's the radial r. So this is again multiplied with r over the capital R. Capital R is the overall radius and varying with time t. Now as per the problem, magnitude of induced magnetic field at radial distance 2 centimeters and 5 centimeters. First we'll write down that r is equal to 3 centimeters. So we need to find out the magnitude of induced magnetic field. So the first case is when r is less than r. So r is equal to 2 centimeters. We'll use a formula that integral closed loop B dot TL, where L is the line element representing for the loop, is equal to mu naught I enclosed. This is the current which is enclosed within the loop. Now as you can see, there is no current as such within the loop in this case. However, there is also another part which is called the displacement current, and we write that as mu naught I T displacement. Now ID is actually represented as, since this part goes to 0, we write this as 0. This is mu naught epsilon naught partial derivative of electric flux over time. And that's our beta. Now considering, so we need to first consider r is equal to this. We have one small loop which is inside at a radius of r equals to meters. Now taking the fact that the magnetic flux in this case is constant along the overall loop, we take b outside, we get the magnitude of b into the TL over along the closed loop. Our closed loop is circular, so the integral is 2 pi r, where r is the radius. This gives us mu naught epsilon naught. The derivative of this with respect to time, t cancels out. Sorry, we do not call it cancelling, so t goes away because of the derivative. R with capital R. Now as you can see, r and r gets cancelled out, so the value of p that we obtain in this case, value of p that we obtain in this case is plain simple mathematics then, and that value is now equal to 3.54 into 10 power minus 17 Tesla. So this can be done by substituting for all the other values. R gets cancelled out, we get a 2 pi 0.6. We'll have to substitute the values of these constant, r equal to 3 centimeters, and then we obtain this value for p. Next we move to the other section. This is when r is equal to 5 centimeters. Now here we will have an interesting part. This is when r is actually greater than the capital R. So we can draw that neatly. Again, we go back to the same formula. We write b 2 pi r. This time r is actually 5 centimeters. It is outside the cylindrical surface. Mu naught epsilon naught 0.6. However, we'll have to now consider what R to choose now. What R should we choose here? Now this represents this value right here. This term actually represents the displacement current. Displacement current is purely due to the change in the electric field flux, and since the electric field flux exists only in this region, so we should also remember that the electric field exists only within this region, which has a radius of capital R. So R can only go all the way from 0 to cannot go beyond that in this case. So this means R over R is just equal to 1, and we get the total net maximum change in magnetic flux, electric flux. So sorry. In this case, we will be using, so unlike the previous case where the R gets cancelled out, in this case we won't have that. R will actually be important, and so our solution will be mu naught epsilon naught 0.6 divided by 2 pi R. This is actually equivalent to saying, now we can also study the whole case by assuming that this is a, you can also assume that this whole structure is actually, and if I want to find out what's the magnetic field outside, I'll consider the entire current which is flowing through the wire, which is only limited till the surface of the wire. But if I want the magnetic field which is inside the surface of inside the wire, I'll have to consider only that part of the wire which is inside and carries a. So, and solution for this is now 2.13 into 10 power minus 17 Tesla.